Gases are generally much less soluble in water than other um, ionic or polar covalent solids because when we look at gases, they tend to be non-polar molecules. And actually, if we do find gases that have a high solubility, it's usually because they actually react with the water around them. So things like carbon dioxide, um, when they are in the presence of water, it actually can form carbonic acid through chemical reaction. So for all gases, the solubility of gas actually decreases as the temperature increases. And if we think about this, it has to do with the fact that at higher temperatures, those molecules have more water, have more energy, and so it's easier for those gases to escape from the liquid. So our enthalpy of solution is exothermic because we don't need to overcome those solute-solute interactions that we do for solids or other liquids. So you probably have experience with this if you've ever taken some soda and you open a warm bottle of soda, it tends to fizz quite a lot. If you open a cold bottle of soda, then you get much less fizz. So as our image demonstrates, if it's warm, that gas is escaping more readily. Our solubility is less than when our gas is cold. We can actually increase the solubility by increasing the partial pressure of the gas that is in contact with the liquid. So if we put it under pressure, more of the gas dissolves into the solution. As soon as that pressure is released, then the gas uh, starts to come out of the liquid. The solubility decreases and less can dissolve into that solution. So when you open a can of soda, you'll see the carbon dioxide bubbles um, start to form as our solubility decreases. So this follows something called Henry's law. So the solubility of the gas is directly proportional to its partial pressure. And that proportionality constant, we'll see lots of constants that are labeled K, does depend on the type of gas that is being dissolved. So this KH, this proportionality constant, is called Henry's law constant. Depends on the type of gas, and so depending on the type of gas, you have to choose the proper constant to use. So let's try an example. Let's figure out what pressure of carbon dioxide is required to keep the club soda at 0.12 molar at 25 degrees Celsius. So we know that the solubility of our carbon dioxide is equal to Kh carbon dioxide times the pressure. So we're trying to solve for our pressure. So we're going to rearrange the equation. Our solubility divided by our Henry's constant is equal to the pressure of our carbon dioxide in the bottle of soda. So we want our solubility to be 0.12 molar. Our constant for carbon dioxide is 3.4 times 10 to the minus 2 molar per atmosphere. And so we can solve this equation and we find that the pressure that we need to have for our carbon dioxide is 3.5 atmospheres. Here's a practice problem for you to try. Pause the video and determine the solubility of oxygen. So in order to determine the solubility for oxygen, again, it is Henry's constant for oxygen times the partial pressure of oxygen. The solubility constant for oxygen is 1.3 times 10 to the minus 3 molar per atmosphere. We know that the air is 1 atmosphere, but because we're trying to find just oxygen, we have to use the partial pressure for oxygen. So I multiply by the 0.21 atmospheres. And we find that the solubility for our oxygen at 25 degrees Celsius, 2.73 times 10 to the minus 4th molar.